So good evening everyone. In our last class we have been discussing about if we are given with a transfer function. So how will we find out the amplitude response of the filters. Okay. Now let us go and look into the different filters. So if you look into the different filters that are being used for any type of signal processing technique, they include low pass filter, high pass filter, band pass filter, band reject filter, and notch filter. While discussing about the filter designing in the analog domain, we have already discussed about these filters. However, why we are discussing over here again? Okay, we are discussing over here again when we are talking about the digital filters. This is because what happens when we talk about the digital filters. So what happens is that, as we have already discussed, that our low frequency, it is the 0, and the highest frequency that is available for designing the filter is pi, and depending upon this, depending upon the fs, the sampling frequency, the maximum frequency at pi, it may vary. Another thing, if you would remember, that we had discussed that when we are dealing with discrete Fourier transform, we said that when we are performing discrete Fourier transform, we get a repetition of the frequency components in the digital domain. Okay, in the digital domain. So if you look into the total frequency component that is available while we are designing the filter, it is 0 to 2 pi radians. Okay, now depending upon the sampling frequency, this 2 pi frequency and pi frequency will vary. Now if you look into the low pass filter, so an ideal low pass filter, it would be something like this. 0 to fc will be having the pass band. This would be the pass band PB, and then fc to pi, it would be the stop band. Okay, now the thing is that we discussed, this is modulus of h of z in the y-axis. Okay, so we discussed that this frequency component, it would be repeating, because digital signals, they are discrete time signals. So what happens, so somewhere over here at the point when we are having 2 pi minus of fc, over here the frequency component, it will be repeating itself. Okay, so this would be again the pass band, and this would be the stop band. See, the bandwidth of the pass band, both in the 0 to pi and pi to 2 pi, they remain the same. Okay, they remain the same. So similarly, if you look into the high pass filters, so what will happen in the high pass filter is, using a similar analogy, we'll be getting this pi, 2 pi, and in the y-axis we'll be having modulus of h of z, right? So this is high pass filter. So we'll be having fc 2 pi minus fc. Okay, so this is the usual pass band frequency components, and the other part marked in, say, blue, this is the repetition of the these frequency components that are available till pi radians. You're getting my point? So in both these things, if you see, there is an repetition of the frequency components in the pi to 2 pi region. Similarly, if you look into the band pass filter, so similarly over here we will be having another this thing 2 pi minus f2, this frequency component, and this would be 2 pi minus of fc1, 2 pi minus fc2 minus here. Okay, so this would be your frequency component, right? Sorry, this would be the c2, this would be the c1, right? Similarly, in the band reject filter also you will be getting similar kind of thing. So till 2 pi, so this would be fc2 my yeah, this would be fc1 minus of fc2 minus of okay. So 2 pi minus fc1, 2 pi minus fc2. Okay. In notch filter, if you see at a particular frequency, there would be a suppression of the frequency component. The same thing will happen over here also. Okay. 2 pi minus fc2. Let's see. Now, after looking into this, now look into the low pass filter design. Okay, so we are having four cases, 1, 2, 3 and 4. So we can generally design a digital low pass filter in four ways. Okay, so there might be some variations of these four filters, but in general we can classify the low pass filter designing into the four categories. In the first category, we just apply a single pole, which is valid, right? So we have a single pole, we place a single pole. Now we look from the top. This is 0, this is pi or FM. So if you look from the top, this is the pole. Now try to visualize. So what will happen? We will be having high frequency component over here near to 0, and then it comes down, and over here also there is a significant, or what you call a finite length is there. So we will be getting some amplitude value. Okay. Now, under usual cases, what happens? Our frequency component, it varies from 0 to pi. Here it was, since we are seeing on the top, on our right it was 0, and on our left it was pi. So we plotted it in this fashion. However, for proper analysis, what we have to do? 0 should be on the left hand side and pi should be on the right hand side. So just by changing the axis, we get this frequency response. Now, what should be the cutoff of the system? Okay, what should be the FC? Now, the FC is defined by a frequency component where the amplitude becomes A by root 2, where A is the maximum gain of the system. Where A is the maximum gain of the system. So, the frequency at which our amplitude or gain of the system, it becomes A by root 2. At that frequency, we will that frequency will be considered as the cutoff frequency. Okay. Now, this is the first way of doing the thing. Now, in the second way, if you see over here, there are some frequency components which will be passing through the system. Now, if you use this, what happens? This same frequency component will be repeating itself. Okay. So when that happens, so the high frequency component, they will mingle up with the low frequency component during the repetition. right? During the repetition, the high frequency components, they will be mingling up. Now that would result in the aliasing. That would result in the aliasing. Hence, to stop that phenomena, in many cases what we do, we apply a zero at pi in the while designing the low pass filter. Okay, so what it will do? It would be similar. You will be having some gain over here, A. Now remember, this gain, this A, it is dependent both on the pole and the zero. You have to find out both the things. Okay, so distance from here to here, you have to find out both the things. In the previous case, it was only the distance of the pole to the frequency component. Say for example, it is 0.9, so it would be 1 by 0.1. However, in this case, the gain would be 2 divided by 0.1. So it is, over here it is 20, here it is 10. So keep this in mind. Okay, when you are putting a 0, it would also have an effect, the maximum gain, what it will be having, it will have an effect on the maximum gain of the system, of the digital system, right? So what happens? It would be 20, the gain would be 20. However, at pi, since the 0 is present at pi, the frequency component would become 0 at that point. Okay. Now, second thing, what you can have, suppose you want a lower cutoff. You want a lower cutoff. Now, what you will do? Suppose you are having one filter over here. I am just developing from here only. One pole over here, one zero over here, but I want a sharper cutoff such that, say, my cutoff frequency is available at pi by 2. Okay, so in that case, what will happen? I will put a zero near to the pi by 2 because I want a condition of a by root 2, because I have told you that the cutoff frequency is governed by the factor a by root 2. Wherever the gain of the system would become a by root 2, at that corresponding frequency, we would call that it is the frequency response. Okay. Now over here, what is happening? I have introduced a zero over here, but if you remember our filter designing criteria, I said that number of poles should be greater than equal to number of zeros. So we need to introduce a pole. Say for example, we introduce the pole at the same position. So we will be having two poles at the same position. So in that case, what we will have, this is not FC1, sorry. So you will be getting a response over here like this. Okay, and this is, would be the say for example Z1. So at this Z1 frequency we will be having the 0, and again at pi we will be having a 0 component over here. Okay, so somewhere here at pi by 2 we will be getting the cutoff frequency. Okay, now what I can do, instead of placing the another pole at the same location, if I move it towards the pi, now see what has happened. The amplitude response, it is getting near to the ideal one, near to the ideal one, right? So again we will be having some ripples over here. So as you place the zero and the pole nearer to each other, this roll off which we discussed in our last class, that would be more and more steeper. Okay, so all of this, if you see what how we are analyzing, we are just analyzing it through the rubber membrane concept. Okay, we have not gone into the mathematics yet. So this is how the rubber membrane concept, it can allow you to analyze any filter response by placing poles and zeros in the Z plane. Okay. Now let us go to the next filters, next types of filter, like the low pass filter. We will be having the high pass filter. Okay. Another important thing, if you see over here, I am not mentioning this real Z and imaginary Z. Okay. But if you don't mention it in your exam, I will deduct marks. So please see, whenever you are this drawing this Z plane, you mark the labels properly. Okay, what is the x-axis, what is the y-axis? Right. Now in the high pass filter, again see there are those four classes we can find out. So just the pole position has changed here. Then in the next place, 0 has been put over here. Okay. In the first case, there was no 0. In the second case, there was 0. In the third case, 2 poles and 2 zeros. In the fourth case, 2 poles have been separated, 2 zeros are there. Okay. So it is similar to the low pass filter, so we should not have any trouble over here. Now coming to the band pass filter, in the band pass filter, the frequency response should allow a specific frequency band to pass. So if you see, there are 2 poles. So this would be the FC1, this would be the FC2. Sorry, this is the FC1, this would be the FC2. Okay, from the you have to find out the FC1 and FC2 through the radius. Okay, so that point and radius, wherever they are meeting, you have to find out the frequency point using that radius. Okay, so the angle over here, it will be giving you the actual frequency point. Okay, angle and the frequency distribution Fs. Now if you look over here, we are having this thing again, there are no zeros over here, so we can see there would be one peak over here and another peak over here. So in between, since there is nothing, and we talked about that there are 2 cones available. So when you are talking about 2 cones, and since these cones are available in this position, if you see, there is a formation of dip, right? Now this dip is nothing but the ripple, and then the amplitude decreases at both 0 and pi. Okay, now there will be leakage of the frequency components, right? Now due to that, you will be having aliasing. To stop the aliasing, we can introduce 2 zeros at both the points. Okay, then for the band reject filter, if you see, if you negate this red poles now, then what happens? You will be getting this blue spectral components. Okay, so it will come like this, it will come like this, and it will again go up. So this is band reject, so this is the stop band. Now if you introduce these 2 poles, these red poles, then what will happen? Since they are nearer to the zeros, the roll-off would be quite steep. Okay, the roll-off would be quite steep. Now coming to the notch filter. Notch filter, it is a combination of low pass filter and high pass filter, and 0 at a particular frequency. So here the 0 has been placed at pi by 2. Now if you want to increase the roll-off, what you have to do? You need to put two poles nearer to the zero. So you will be getting frequency response something like this, right? Are you getting my point? So what is happening when we are placing the pole nearer to the zero, our roll-off it becomes quite steeper in nature, right? Now coming to the radial positioning, while discussing about the placement of the poles and zeros in the S-plane, we discussed that when we place the poles or the zeros across the real axis, there would be a change in the amplitude response. Nearer to the frequency axis, the pole is, the more pronounced will be the effect of the pole, and the same goes with the zeros also. Nearer the zero towards the frequency axis, the better would be its effect onto the frequency. Okay. The only difference was that we could have placed the zero onto the imaginary axis. However, we cannot place the pole on the imaginary axis. It has to be slightly away from the imaginary axis on the left hand side. Okay. Now the same thing, if you try to put in here, so what happens? The real axis distance, it now becomes the radius. Okay. It now becomes the radius. So the left hand side of the S-plane, it maps within the unit circle, right? It maps within the unit circle. Now what will be the omega naught of a particular filter? It would be decided by the angle of the radius, by the angle of the radius. Okay. And what is the frequency axis? The unit circle is our frequency axis, right? Now let us take three cases where pole is present at p equals to 0.9, p equals to 0.5, p equals to 0.3. Okay, let us take these three cases. Okay. In these three cases, what happens is that, say for example, we all say that there is a zero over here, so we will put at pi the frequency response is zero, say for example. Okay. Now the thing is that if you look into when p equals to 0.9 and we will look into the DC frequency at this moment. So at zero frequency, what happens when p is equal to 0.9? The gain becomes 1 by 0.1, which is equal to 10. So the amplitude it becomes say 10 over here. In the case of 0.5, 0.5, so 10 by 5, gain is 2. So gain becomes 0.2. In the other case, when p is 0.3, it becomes 1 by 0.7, 10 by 7, 1.4, 1.4 something. Now if you see what is happening, as you are placing the pole nearer to the frequency axis, our gain it is increasing. Okay, and as we are moving towards the origin, the gain is decreasing. In the similar way, if you look into the z, the zero, where 0 is equal to 1, 0 equals to 0.5 and 0.3. So in the similar way, what will happen, we'll be having gain due to 0. At 0 it will be always 0, but at pi, what we will be having? In this case 2, in this case 1.5, and in the last case it will be yeah, 0.3, 1.3. Okay, so this is at pi. This is at pi. Okay. Now at 0, what will happen? 0. What about this? 0.5, 0.7. Okay. So what happens over here? If you see 1, it is having the lowest this thing gain. At 0.5, you are having the slightly higher gain, and then at 0.3 we will be having the 0.7. Okay, so this is at the DC frequency, and at higher frequency at pi we will be having this thing. Now if you normalize this, we will be getting something like this. Okay, if you normalize the gain. So if you see, just by the placement of the poles and the zeros, we are able to manipulate the thing. Okay. Now if you look over here, we are slowly getting into the mathematics of digital filter design. Right? Now let us take that our zero this have been provided at z equals to minus 0.9, and poles it is present at 0.9 and 0. Now how will you find out the transfer function of the system? The transfer function of the system, it is given by hz equals to z minus of minus 0.9. Okay, it becomes plus divided by z minus of 0, which is basically z, multiplied by z minus of 0.9. Okay, so from here we will be performing the pole 0 plot analysis. Okay, now if you have to implement it, so what is the degree of highest degree or the order of the numerator or the denominator? It is z to the power 2. So we have to multiply the numerator with z to the power minus 2 and z to the power minus 2. Then we get to this equation. So this equation where we are having this z to the power minus this operators. So that equation will be needed while we want to implement the filter. At this moment we are not implementing the filter, so you can just keep it how to calculate it and just keep it aside. Okay, now next comes at h equal hz at 0 frequency, what would be the gain of the system? It is say 1.9 for the 0, because 0 from here to here it is 1.9 divided by 1 from here to here, and from here to here 0.1. So you get a gain of 19. Okay, at pi what you get? 0 to here 0.1, 1 into 1.9, so it is 0.05. Okay, so at DC frequency 19, pi, that is the maximum frequency, we are having 0.05. So what type of filter it is? Yes, Vishwajit, कितना सोओगे? So what type of filter it is? It is a low pass filter. Okay, now next see over here. Now what we have done, we have z equals to 0 is present at minus 0.9 and pole is present at 0. So this pole we have vanished it. Okay, so the gain at 0, see 1.9, it remains the same, because what happens is that um, yeah, this 0.1 factor uh, it is not here, and that's why what has happened, the gain has come down significantly. Okay, However, if you look into this pi at pi, so we are having a gain of 0.1. Okay. Now, if you compare these two, this is higher. Why this is higher? Because in the second case, we are not having an extra pole. And since we are not having an extra pole, the 0 is getting more predominant in nature. Okay. When you put extra poles, effect of the poles, it gets strengthened. When you put more of zeros, the effect of zeros, it gets more prominent in the frequency response. Okay. Now, in the third case, see, minus of 0.9, 0.9 we have kept. Okay. And 0.9 and 0, the poles are at the same position. So basically what we have done, we have put an extra 0 at the location 0.9 where there was already a pole. Okay, where there was already a pole. Okay, now if you see the HZ, it becomes this one. Now you will be very much intrigued looking into this equation that we should cancel this one. Okay, when you are given with the poles and the zeros location, or you are given with the transfer function, and if you have to implement, you would be very much intrigued to cancel out these things, but do not cancel. The reason being, in the actual equation what you will be deriving for the implementation of the filter, if you cancel this out, so what happens, the degree becomes 1, degree of the filter becomes 1. So in during the implementation you will be implementing a single order filter. Okay. However, if you want to find out the amplitude response, in the amplitude response and also in the this phase response, you can cancel that out, but during the implementation you should not cancel out the components which are present both in the numerator and the denominator. Okay, now considering this, if you look the amplitude response, if you see in the second case and in the third case, whatever we are having, these values are getting replicated. These values are getting replicated. Why? Because we have already discussed previously, when we are putting a pole over a 0 or a 0 over a pole, they cancel each other's effect. Okay, and this example was to show you this thing. So if you put a pole over a 0 or a 0 over a pole, they will cancel each other's effect. Okay. In the next case, if you see what happens if we place a pole over a pole, यहाँ पे देखो these are same, we have just added an extra pole. Now if you see the effect, कहाँ 19 था, where it becomes 190, here it has come down. Okay, so pole over a pole would improve the amplitude response at the what you call omega naught. Okay, at the omega naught. Similarly, if you are talking about zeros, it would be 0 over, if you place a 0 over a 0, it will suppress the frequency component at the omega naught position. Okay. Now this is what it has been shown over here. same position. सिर्फ आप देखो we are putting one extra zero near to this line. यहाँ पे because you have put extra zero, it will definitely affect the other frequency, because what is our omega naught? Omega naught is present at pi. Now if you look at pi, there is a 10 time reduction in the amplitude response. Getting my point? Now suppose I tell you, you find out what is the phase response of the system. The phase response of the system is being find out from here. How do you find out? Hz, I'm giving it with a simple example, but the same thing goes in all the other cases. Hz equals to 1 by 1 plus Az inverse. Okay. Now we are interested only in the frequency axis, which is nothing but your e to the power j omega t. Okay. What is your e to the power j omega t? It is nothing but cos omega t minus j sin omega t. Okay. So what you can do is that you can put this equation in this format. Okay. So what you get? You get this thing. We can put it in the form 1 by a minus jb multiplied by, if you multiply with the conjugate, you get a plus jb divided by a square plus b square. Now it can be represented in a plus jb. Okay. Now you find out the modulus of this one. It is nothing but under root of a square plus b square, and this is your phase response. Okay. Here your a has been taken as the what do you call, 1 in this case. Okay. So that's why you are getting, you're not getting this thing, so we have considered that as 1. So what we have done, basically the real components have been taken together so that we can arrive at this in this form, and we can convert it into the a plus jb format. Okay. So whatever we have been doing by measuring the distance, it the same amplitude response can also be found out by this mathematical formula, uh, under root of a square plus b square. Additionally, we can also find out the phase response of the system. Okay. So with this we complete the thing, this chapter. So for the phase response, if you see, we have already discussed in one of our classes what formulas you will be using. Okay.